Hello and welcome to my first lesson on Trigonometry 3. In this lesson, I want to meet the following objectives. First of all, I want to be able to derive the trigonometric identities. The one that's written there, sine squared plus cos squared is equals to 1. Again, we should be able to draw graphs of trigonometric ratios in the form of y is equals to sine a in brackets bx plus or minus theta, and again y is equals to a cos in brackets bx plus or minus theta, and therefore we should be able to deduce the amplitude, period, and phase angle for in those particular questions or graphs. Lastly, we should be able to solve trigonometric equations graphically and analytically. And maybe before I start, I need to mention a few things. The first thing I need to say is to be able to meet these objectives, I'll need to take you through some concepts that I find necessary and prerequisite to Trigonometry 3. That is, some concept in Trigonometry 1 and another one in Trigonometry 2, which is very much related with what we have here. And another thing I should also mention is that in my lessons, I normally don't tackle every little thing in the syllabus, but I tackle what I think is necessary, and I try to tie the concepts together so that I don't have to say it too much to confuse people, but I say just what is necessary and to be precise in that particular way. Now, the last comment I want to say is, in this particular lesson, I will only be able to meet the first objective. I should be able to derive this trigonometric identity in the first trigonometric identity I have on the screen there, this one here. The others two will be following in the lessons that will be just after this. And so maybe having said that, we need to begin. Now, we need to recall from the definition of trigonometry, if we have a right angle triangle like ABC, we normally have, if this A meets or describes this particular angle, and B describes this particular angle, and C describes the right angle, then the opposite sides are normally represented using the same letters but small letters. In this way, the angle A is exactly opposite to small a. So the side and the angle being opposite to each other, they are all represented by small letter A and capital A, where the side is small letter A and the angle is capital letter A. The same case, C is an angle, the capital C is an angle, and the side that is opposite to that is represented by small letter C. The same thing with B. Capital B is an angle, but B, small b, is representing the side exactly opposite to B. Those are just some certain thumb rules for trigonometry 1. Another thing I need to mention is that B is exactly opposite to, the small letter B, that is a side, is exactly opposite to given angle theta. All right. So what I'm trying to do is identify the three sides A, B, and C from definitions of trigonometry. So B is opposite to theta. A is adjacent, the English word meaning right next to. So the angle theta, the length, the side A is right next to the angle theta. And from earlier concepts, we know that AB is hypotenuse. Now, A and B, that is the adjacent and opposite, are perpendicular sides of right angle triangle, and AB, that is the side marked small letter C, is a hypotenuse, which is normally the diagonal. So, well, all triangles have three sides, but right angle triangle normally has two sides which are perpendicular, and in trigonometry, the two perpendicular sides are either opposite and adjacent, depending on where the angle is placed. And of course, the third longer side is hypotenuse. Now, as we go ahead, I need to say this, that in a trigonometry 1, we say that sine theta, that is sine of this angle, normally relates the opposite side and hypotenuse. So we would say that this side divided by this would give us what we call sine theta. So sine theta is equals opposite of a hypotenuse. Okay? It's a trigonometric ratio that relates the opposite and hypotenuse for any given right angle triangle. So the angle made at this point here will always be opposite divided by hypotenuse. I need to mention that SOH is used as an acronym or abbreviation to representing the S representing the S for sine, the O representing O for opposite, and H representing the O for hypotenuse. So this is just a way of ensuring that students can remember that with ease. So if you are struggling, sine is equals to what? You should always say SOH, meaning sine is opposite of a hypotenuse. The next thing I need to mention there is cos theta is the second trigonometric ratio which relates the adjacent to the hypotenuse. And we normally say that for any given angle in a right angle triangle, cosine of that angle equals to the adjacent side divided by the hypotenuse. I cannot say that any better. Again, the acronym for that is CAH. C standing for the C in cosine, A standing for A in adjacent, and H representing the H in hypotenuse. The last trigonometric ratio, which is tan theta, is equals to opposite over adjacent. So for any given angle in a right angle triangle, in a trigonometry, we normally say that tan or tangent is normally equals to opposite over adjacent. Allow me just to put it simply as that, and now say that the acronym is TOA, which is tan is equals to opposite of adjacent, T meaning T for tangent, or this O meaning O for opposite, and A is A for adjacent. And so that way we just have the basic definition for what trigonometry is all about. To help us remember, we normally say SOHCAHTOA, and so the SO is sine is equals to opposite of hypotenuse, CA is cosine is equals to adjacent of hypotenuse, and TOA is tangent is equals to opposite of adjacent. Maybe to tie this all together, I need to mention some two things. One thing, whenever you're given a right angle triangle and it's related with concept in trigonometry 1, we should always be able to identify which side is opposite, which side is adjacent, and which one is hypotenuse. Why did we say this is opposite? Because it is exactly opposite to the given angle. If the given angle was at A, then what we have as adjacent here would be opposite. And of course, this would be adjacent. The opposite would be adjacent. So we should always be able to identify what is opposite and what is adjacent. The hypotenuse is always easy to identify because it's the longer side. It's also unique in that it's not perpendicular to any other. So that is easy to notice. Anytime you should be able to identify what is opposite, what is adjacent, and what is hypotenuse. The last comment I want to say is that we should be able to solve sine, cosine, and tangent for complementary angles. What I mean is there are only two places you can place theta here. This is the point where theta is, and also at the point A. So we should be able to solve any the sine, cosine, or tan of complementary angle. If theta was here, we should be able to say that sine is equals to A over C. If theta was also there, we should be able to say that cosine is B over C, tan would be A over B, and on and on. We should be able to do that. And that's basically to refresh the concepts that we have in trigonometry 1. Another thing we need to recall is a unit circle. Now this one comes to us from trigonometry 2. And you remember this kind of a thing? I hope you do. We have a diagram that elsewhere is called the Aggregate Diagram. We have the 180 to 360 is the equivalent of the x-axis, and 90 to 70 is equivalent of the y-axis, and we have a circle there. Now we use this one to define so many other things, so many other concepts that have to do with the looking for trigonometric ratios of all angles from 0 to 360, or even bigger than that, or even negative angles. So we use this diagram to be able to define that, and I'm going to tie the concepts together in a short while. And so as we begin, I need to say this. We normally have the first, second, and third quadrant, and fourth quadrant. First, second, third, and fourth quadrants. What this means is that this diagram can be divided into 4 quarters, where the first quarter is representing all angles that lie somewhere between 0 line, this, and 90, from 0 to 90 degrees. The second one is from 90 to 180. The third one is from 180 to 270. The last one is 270 to 360. So this diagram can be divided into 4 quarters, which are, as I have said there, first between 0, angles between 0 and 90. The second one being angles between 90 and 180. The third one being angles between 180 and 270. The last one is angles from 270 to 360. So this one gives us an ability of identifying or looking for trigonometric ratios of all angles between 0 to 360. The next thing I need to mention is that as I have taken you just previously there, all angles are measured clockwise. Sorry, anti-clockwise. I should insist that anti-clockwise. In mathematics, anti-clockwise is positive. So we are moving anti-clockwise from 0 to 90, then 90 to 180, 180 to 70, to 70 to 360. And that means whenever we have a negative angle, it's because it's measured anti-clockwise, and we should be able to transform it to be clockwise and identify in which quadrant it lies, and then look for the trigonometric ratio. I might not be able to go through that. Maybe in a lesson in future, I should be able to take you through details of trigonometry too, but let me just say that for now. The next thing I need to say is when we are looking for trigonometric ratios in the first quadrant, we just look for the angle as it is, and they are always positive. So if it's an angle in the first quadrant, it will be sine theta or cos theta or tan theta. I don't have a lot I can say anything more than that. In the second quadrant, we will also look for theta. I'll show you how to convert shortly, but we look for sine theta, and we should know something, that sine is positive but cosine and tan are negative. All right, I've typed my presentation such that all the angles that are positive, I put them in green, and all the ones that are negative, I put them in red. So in the first quadrant, all the three trigonometric ratios are positive. In the second one, only sine is positive. In the third one, sine is negative, cosine is negative, but tan is negative. Tan is positive. The same way, I would say that quadrant, sine is the fourth quadrant, sorry. The fourth quadrant, sine is negative, cosine is positive, and tan is negative. Just in case I say something that is not here, look at what I have typed there, and it will give you a summary. I'll also give you a summary at the end so that I'm not confusing you with too many concepts. So having said that, I need to move on to another concept that I think is necessary. All angles between 0 and 360 should be transformed to be an equivalent to an angle in the first quadrant. In other words, if we are given an angle and it's not in the first quadrant, we should be able to perform a certain operation which gives us an equivalent angle to the first quadrant. All right, and as I illustrate that further, I would say this: if we are given an angle that is somewhere between 0 and 90, and we are looking for the trigonometric ratio, we should just type sine or cosine or tan of the given value, because it's just between 0 and 90. However, if it's in the second quadrant, we should transform by having 180 minus theta. I need to pick my pen here and maybe illustrate that. Say for example, we have an angle like that one there. We have an angle like that I have drawn there. We should be able to transform this angle to be an angle equivalent to those between 0 and 90. For example, if this is 120 degrees, we'll transform by having 180 minus that given 120, so that we get an answer that's somewhere between 0 and 90. In our case, it will be 60. Okay, so that should be clear there. We transform all angles in second quadrant by subtracting that given angle from 180. The reason is all angles are always measured from the 180 degree line, so we are trying to change it to be that way. Let me not say a lot there. The next thing I need to say, which is now on the third quadrant, is that all angles will be transformed by having theta minus 180. Again, that way we will be able to transform the angle to be an equivalent to the one between 0 and 90. And for those of you who know, in the last quadrant, we would have theta minus 360. Remember, all times we are subtracting so that the angle is measured from the 0 to 180 degree line, and again, at the same time, the angle will also be equivalent to an angle from 0 to 90. Maybe in some subsequent lesson I'll be able to do that, but not at this time. The next thing I need to mention is that to summarize that those concepts for you, I've removed all of those things there, and I want to illustrate the summary. 1. All angles are positive from 0 to 90. I've just said that. All angles from 0 to 90 are positive. Only sine is positive from 90 to 180. That means cosine and tan are negative. Another thing is that tan is the only one that is positive for an angle that is between 180 and 270. That means sine and cosine are negative. And of course, cosine is positive for all angles between 270 and 360. That means sine and tan are negative. Another thing, I need to say that in the first quadrant, we just use the given angle as it's given. Say 20, 30, 40, whatever angle it is. Since it is just between 0 and 90, we just use it as it is. But in the second quadrant, we normally subtract 180 from that given angle from 180. The next one, we have the theta minus 180. And the last one, we have 360 minus the given angle. So that is it. Now, to tie those things again, or just to repeat myself in a different way so that I illustrate things, I need to say this. There are some necessary questions you should be doing whenever you're doing questions that have to do with all of these concepts in the unit circle. Number 1, ask yourself, when is a trigonometric ratio positive? Now we know that sine is only positive in the first or second. We know that cosine is only positive in the first and the last. We know that tan is positive in the first and the third. Another question you should ask yourself is, how do we convert angles in the 4 quadrants? For the first quadrant, we don't convert anything. The second one, we just have 180 minus the given angle. The third one, we have the given angle minus 180. The last one, we normally have 360 minus the given angle. And that summary is again presented here. If this table here represents the first quadrant, second quadrant, third quadrant, fourth quadrant, all angles are positive in the first one. There is no conversion in the first quadrant. The second one, only sine is positive. We convert by having 180 minus the given angle. The third one, we convert by having theta minus 180, and tangent is positive, meaning the other two are negative. The last one, we normally convert by having 360 minus theta. Only cosine is positive. I've repeated myself so many times in different ways so that the concept is clear. We will use this concept to tackle questions in the last objective that I gave in the beginning. And so when we go there, we will refer to this a lot more. Well, now let's go to the first objective. The first objective was to be able to define some 2 trigonometric identities, to derive them. And so let's begin. Now, from this given triangle, we have the sides A, B, C. That's the triangle ABC, with the sides small a, small b, small c as is given there. Now, we normally know that sine is equals to opposite of a hypotenuse, which is b over c. That is, sine of this angle is opposite side divided by the hypotenuse, which is b over c. If we cross multiply that is multiply c both sides, we get c sine theta is equals to b. C sine theta is equals to b. Just multiply both sides. This c cancels with the c that comes here, and again c comes before the sine theta. So we have c sine theta is equals to b. And that means where we had b here, it can be also replaced by c sine theta. Subsequently, we can do this, that since we know that cosine theta is equals to adjacent of hypotenuse, that is cos of this angle is equals to a all over c. If we cross multiply c both sides, we get c cos theta is equals to a. And that means that where we had a here, we can replace it with c cos theta. That means the side AC is c sin theta, the side BC is c sin cos theta. There's another thing I should say, that the two perpendicular sides of a right angle triangle, they can be replaced by c sin theta or c cos theta. And you should know that the opposite is always related with sine, the adjacent is related with cosine. So don't mix up things. When you're looking for, say, when you're looking for cosine, we don't use the opposite anywhere. No wonder. That's why we have the adjacent replacing. No wonder we have the adjacent being replaced by c cos theta. And also, again, when you're looking for sine, we don't have adjacent anywhere. We only have opposite. So the opposite is again associated with the sign. I don't know if I can say that any better. So having said that, now we go to another aspect. We also know that tangent is normally given by opposite of adjacent. In other words, tan of this given angle is B all over A, like I have indicated there. That means tan theta is equals to C sine theta divided by C cos theta, and it's indicated there, right? This one here. What does that tell us? If we can cancel the C's, since they are appearing on the numerator and denominator, we are left with the first identity, which is tan theta is equals to sine theta over cos theta. If you have forgotten everything else I have said there, just master this. For all angles in mathematics, tan of that given angle is normally the same as sine of that angle divided by cos of that angle. And that is that. It is true for all angles in mathematics. Let's go to the next thing. The next identity will tackle it using a concept that is related with Pythagoras theorem. And now we know from Pythagoras theorem that a squared plus b squared is normally c squared for a right angle triangle. That means the two parallel sides, if you square them and add them, you will get the third one squared. And that's what we have there from Pythagoras. Now, that means, since we say that this is c cos theta and this is c sin theta, we can square it. That is, we square this one, and you get c squared from what you just have earlier there. And that means, now if you square this or simplify it, it'll come to this. You see, the c will be squared, so it becomes c squared. The cos theta will be squared, which becomes cos squared theta. Again, c squared will be c squared there. Sin theta will be squared, so we get sin squared theta, and of course c squared there. The next thing we should know is that we can factorize out the c here, the c and the c here. So get it out, you get c squared outside, and then within our brackets we have cos squared plus sin squared, and that equals to c squared. And we can divide both sides by we can divide both sides by c squared. So we divide this by c squared and also this other one by c squared, and therefore that gives us 1. You see that? So before the equal sign, everything goes, but we remain with cos squared theta plus sin squared theta. After the equal sign, we are only left with 1, and that one gives us the identity that I needed to emphasize. And here it is: cos squared theta plus sin squared theta is equals to 1 for all angles in mathematics. It doesn't matter what the value of that angle is. So I have finished my first objective. I wanted to take you through tan theta is equals to sin theta plus cos theta. The second one was cos squared theta plus sin squared theta is equals to 1. If you go to the syllabus, the next thing that happens after defining these two is trying to prove some identities. I will not go to that because I think every identity is tackled, every proof is done different from any other, and the whole idea that students should know is this one. And if I show you one today, you might not be able to use even that concept again. What is necessary to know in the case of proving those identities is just these two identities. Manipulate them in so many ways. I'll not go into that because of some constraint, but I will take you to trigonometric waves and solving trigonometric equations graphically and also analytically. And having said that, I wish to express my gratitude for watching my tutorial. I'll appreciate your comments. Thank you.